everyone. My name is Tom Johnson, and I'm the director of the EOGOGICS Web Live program. Having been involved in computer-based training in one form or another for more than 25 years now, it's my pleasure to welcome each of you to this Web Live session. For those of you who may be new to EOGOGICS, I'll refer you to the About EOGOGICS page on our website. Suffice to say that the EOGOGICS team, led by KK Aurora, has been involved with many landmark telecom projects worldwide during the last 20 years or so. In fact, I think KK is with us in our audience here somewhere. KK?
I am. Thank you, Tom. Good morning or good evening, as the case may be, and welcome to the class.
Thank you, KK. Always good to have you with us. And now, let me introduce our presenter today. Frank Wortman is a principal member of the EOGOGICS Telecommunications faculty. You can view his detailed bio on the website, but I'd like to say a few words by way of introduction. Frank teaches the EOGOGICS courses on 4G, WiMAX, Wi-Fi, SIP, and VoIP. He also provides consultation on RFP design and vendor selection to those involved in implementing broadband networks as part of the BTOP program that's included in the U.S. Economic Stimulus Act. Frank's teaching and consulting career builds on his 20-plus years experience in telecommunications and in electronic warfare. A firm believer in learning by doing, he even operated a small WiMAX network for a while. An interesting tidbit there. Frank has published several research reports and 4 books covering topics such as WiMAX, Wi-Fi, Voice over IP, and the emerging all-IP architecture. And now, without further ado, Frank Wortman.
Thanks for that thrilling introduction, Tom. Let's move through a quick housekeeping note on intellectual property rights, which remain the property of EOGOGICS. If you need to borrow some of the content of this, feel free to contact us at the contact information below to discuss that. Well, today's presentation is on LTE for all audiences. And I want to begin this with the context of kind of asking that open-ended question, why your smartphone doesn't work the way you think it should, and use that to drill down and discuss how LTE works and the place in the marketplace. First of all, we should discuss what is 4G vis-a-vis LTE. 4G, or fourth generation, is the marketing term. It's not a standard such as one would find with the IEEE or others. LTE, or long-term evolution, is a standard developed by the 3GPP working group, which is a consortium of cellular vendors, and of which many acronyms are in most of their materials. However, all have a path to a common goal. That is more bandwidth to the subscriber than one might find with 3G or third generation. It's mostly considered mobile, if not being very mobile, depending on some of the different proposals. It is all IP, or flat in its architecture, that is Internet Protocol. Everything is Internet Protocol, and which would indicate there are no circuit switches involved here to deliver voice. That is all voice over IP. We hear a lot in the press today about smartphones and problems with dropped calls. Downloads may not be as fast as the subscribers think they should be, even though the service is advertised as being third generation. And this leads us to the question, are the devices here, but perhaps the network is not? So most of what we're going to talk about over the next 2 hours is what has to happen before smartphones can perform as we think they should. Let's start off with a discussion of the legacy cellular architecture, or should we say the cell phones for everybody. I'm going to start at the right-hand side of this slide and talk about the network as a whole. And we start out with what the service that we've come to take for granted, a very reliable sub-8 kilobit voice channel, highly compressed voice. For you telecom groupies out there, we all know that per Bell Labs, telephone conversation over copper wire has a bandwidth of 64 kilobits per but in order to make a cellular network function correctly, starting back in the 80s, they used compressed voice. So taking that 64 kilobit channel, compressing that voice down to something less than 8. Maybe it's 6 kilobits, maybe it's 4 kilobits, depending on the service provider and the location. Then we connect to a base station, which also has a mobile switching center, which in turn connects to the larger network, the public switch telephone network, via copper wire in these cases. At least 80% of base stations and cellular base stations in the U.S. connect to the public switch telephone network via copper wire. We also call this the middle mile or backhaul to connect back to the telephone switching center, also known as the central office, as described here on the left-hand side of the diagram. Central offices date back to the very earliest days of telephone switching and are comprised largely of telephone switches. And I should also point out the three categories to greatly simplify legacy cellular architecture. And again, if you look at the top of the slide, moving from right to left, we have the radio access network, or RAN, also known as last mile. Then we have our middle mile, also known as backhaul, and then the core, where all the switching and the management, the provisioning, and those sort of managerial issues are administered. So how would we move from that legacy cellular infrastructure to a 4G? That is the move from third generation to fourth generation. So starting at the last mile, we'd move in either LTE or its competitor, WiMAX. At the middle mile, we'd have to boost the capacity there as well and make significant changes at the core of the network. So this diagram shows a hypothetical 4G network, fourth generation network. And the question should be, well, how do we get there, and what is it we're going to have to change in the legacy cellular network to get to a 4G network? And moving again from right to left in the radio access network of the last mile, we'll have to change out the base station radio or add a WiMAX or LTE base station radio and its associated antenna or antennas in order to provide the wireless service to the last mile. We will also have to make some significant adjustments in the spectrum, that is for the electromagnetic transmission between the subscriber and the base station. And very concretely, moving towards the center of the diagram, we're going to have to do a lot with backhaul or the middle mile. So we need to replace the copper wire in there. And we hear a lot about fiber optic cable, although maybe 20% of base stations in the U.S. are connected via fiber optic cable. This leaves us looking for a cost-effective solution to replace that copper wire, and most of that is seen as being wireless, be it licensed microwave or gigabit Ethernet that can, as the name might imply, deliver a gigabit of throughput to the base station. And then moving to the left at the core, if we're all IP and we're not dependent on the telephone company's central office for its circuit switching, we can connect to any fiber point of presence, which in turn connects us to the IP backbone, i.e. Internet, but we're still connected to the PSTN if we need to be. So here's a diagram of pointing out some of the significant advantages of LTE, and most of which, if you're a smartphone user frustrated by slow downloads and poor data performance, you're concerned about your throughput. And as the green circles indicate, these are the projected